Sweet. All right. We're going to talk about resonance for this one. It's a little bit weird. Let's just kind of baby step our way into this as we go. All right. So let's talk about ozone. Ozone is O3, and we want to draw. Let's draw a good Lewis structure for ozone. So we'll know each oxygen has 6 valence electrons, and there's 3 of them, so we have 18 total, which means we have to keep track of 9 pairs. Okay, 1. Okay, 3 O's. That's all we really can do at the start. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. Okay. Now, if we look at this, these dots are stressing me out. If we look at this for a little bit, we'll realize this is not good because the central oxygen does not have enough electrons. So we need to share and make a double bond from one of the outside ones. So I'm going to do it from this side, get rid of those dots, and make a double bond on this side. Okay. Now, you might be thinking, why did I choose this side? It doesn't matter. I could have chose the other side. Okay. You could do either one. And both of these are valid Lewis structures for ozone. Okay. The downside is neither of these is correct. And the actual structure of ozone is it's actually both of these things at the same time. Okay. And the reason we know this is because experimentally, all of the bonds in ozone are the same. Okay, so this is really what's tipping us off. Experimentally identical bonds, which means they have the same length and the same strength. If we're thinking about this, switch colors here. This should be a bond order of 2, and this should be a bond order of 1, in which case, based on what we've talked about before, we would say that the single bond order, the bond 1, is longer and weaker, and the bond 2 is shorter and stronger because that's what the bond order tells us. However, there's not one that's longer or shorter, and there's not one that's stronger or weaker. They are the same idea. And it turns out they're the same idea enough that they are between an OO double and an OO single. And they act like about a bond and a half. If you look at it distance-wise, that's what makes sense. What's happening here is this idea of resonance. Okay. We also call this delocalized bonding. Resonance is an example of delocalized bonding. And what we're seeing in our ozone is we're seeing that we're sharing 2 electrons between 3 atoms. So that double bond isn't necessarily just between 2 of them, it's amongst all 3. Okay. And the molecules do this because this is more stable, it's a lower energy situation, and so it's easier for them to come up with that. This is me, I just drew it this way so that you didn't have to suffer with me drawing it again. These are what we call resonance structures. The resonance structures represent the delocalized bonding. Okay. This is one of the failings of Lewis structures because there's not one good Lewis structure for ozone. We could draw something along the lines of this, like a hybrid structure if we wanted to, but it's kind of hard. So what we have to do here is we just have to make a mental, I call this a mental mush. It's a mental mush of both resonance structures at the same time. So the double bond isn't just here and here, it's both places at the same time. And this lone pair isn't just here and here, it's in both places at the same time. This is how the delocalized bonding works. Yeah. We can also think about the bond order. Remember we said here that it's somewhere between a double bond and a single bond. We can actually figure out the bond order when resonance is happening, when we have delocalized bonding, by calculating it. Okay. And we can think about it as how many electrons are we sharing and how many connections do we have? So here we know we're sharing 2 electrons and we're sharing them between 3 atoms. So this is 1, 2 connections. Okay, so here for ozone, our bond order is going to be equal to 2 electrons shared. Oh, total. Don't be stupid. 1, 2, 3 pairs. So 3 pairs divided by 2 connections, or 3 halves, or we could say 1.5. Okay, sorry, my office phone is ringing and I'm not going to answer it. Actually, maybe I'll do that. Let me pause. Alrighty, so we can think about bond order this way, right? Because it's somewhere between a 1 and a 2, it's 1.5. Okay, let's look at another example. Where'd my clicker go? There we go. Okay, let's look at carbonate as we do this. Okay, let's think our way through this. So draw a valid Lewis structure, and we want to look and see if there's resonance structures involved. There's going to be, because yeah, spoiler. Okay, so carbon in the center, we'll connect 3 oxygens to it. I like doing it like this. Yes. Okay. We give everybody 6. This way everybody has 8. I should count up my total electrons first. Give this guy brackets and charge. All right, so this is 4. This is 6 times 3 is 18, plus 2 more is 24. So we've used all of our electrons here. Notice our carbon in the center is pissed off because it doesn't have 8 valence electrons. It has 6, so we need to give it 8. And to fix that, we're going to need a multiple bond. So I'm going to take these guys and I'm going to share it. Okay. Why did I choose that one? Because it looks nice. It's symmetrical and it looks pretty to me. Okay. It doesn't matter, right? This is how you know you're going to have resonance structures, is because you're going to have options for where the double bond goes, right? So when we look at this, we're going to find, when we're looking for resonance structures, there are going to be options, okay, where they're all equally reasonable. Okay. Now, the nice thing about this, okay, I want us to draw all of the resonance structures for carbonate. Okay, I have this one. Let's make it look nicer. Okay, once we have our good Lewis structure that's the way we like it, like this guy, okay, then the other ones are exactly the same, but they're the other options. Okay, so in this one, we did the bond going up. So in the other ones, we're going to draw the bond on the other side. So here we can draw the bond going this way. And everything else should look the same. Okay, give it brackets and charge. Okay, so that was up. This is to the left. This one needs to be to the right. Okay. 6, gosh. There we go. 2 minus. All right. Not too terrible. Let's think of this. Okay. Notice what we've done here is the resonance structures are only different by how we've arranged the electrons. Okay, that's crucial. Only the electrons are different. Okay, the same total number of electrons are there. The atoms are in the same general location. The bonds are roughly the same idea. Okay. Oh, let's calculate the bond order for this. Okay, so we want to think about how many pairs shared, number of electron pairs shared, divided by the number of connections. Okay, so here we've drawn a total of 4 lines between carbons and oxygens. So that's 4 pairs shared. We've connected 3 connections, right? 1, 2, 3. Okay, so this is 4/3 bond order, or we could say this is 1 1/3, right? You could call it 1.33333, whatever, but 1 1/3 looks fine to me, so we'll just leave it like that. Okay. Yeah, and we're going to talk more about resonance later on. It's not a huge thing in Gen Chem 1, but we want to be able to recognize that it exists and pick out some stuff and draw resonance structures and all that kind of fun stuff. Other things that do resonance, Benzene is a good classic example. Um, we talk about this in organic chemistry a lot, and we'll talk about resonance a lot when you get into organic chemistry. But um, benzene thwarted chemists for a little while because they knew it existed. They knew it had a formula of C6H6, but they couldn't think of what the structure was to make it make sense. Ultimately, it was a guy by the name of Kekulé who came up with the idea of it being a ring. And so technically oftentimes we call this the Kekulé structure of benzene. And it has two resonance structures. These three double bonds could be in either orientation. As long as they're every other one, we're not violating any of our rules for Lewis structures. Okay. And we're going to talk about a little bit about why this happens later on. Okay. If you have any questions or you need anything, let me know and I'll catch up with you later.